Exactly 14 billion years ago, the Big Bang erupted. The universe went from utter void to a rapidly expanding, heated cosmos. In those initial fractions of a second, this newborn space was an infinitely dense furnace. The ambient temperature and pressure were so extreme that ordinary atoms could not possibly exist. Instead, the space was filled with a chaotic ocean of pure energy. Out of that blinding plasma emerged the very basic components of matter, quarks. At this stage, it was entirely too violent for these newly born quarks to build anything. They simply swam freely through the plasma, crashing alongside other raw particles like electrons and photons. But the universe did not remain compact. It expanded outward violently, forcing that dense, trapped plasma to begin dropping in temperature. If the universe had stayed perfectly hot and dense, those quarks would have remained suspended and isolated indefinitely. By stretching out and cooling down, the cosmos created the conditions required to build physical structure. This crucial drop in temperature brings us to the quark epoch. It was an incredibly brief window of time, occurring between roughly 10 to the negative 12th and 10 to the negative 6 seconds after the Big Bang, where the local physics shifted. As the heat dissipated, gravity and the strong nuclear force took over the plasma, acting like a powerful glue on the previously free-floating particles. Two specific types of these particles, called up quarks and down quarks, began slamming into one another. When they collided, the strong force snapped them together into tightly bound, inseparable trios. The combination followed a strict mathematical recipe. Two up quarks and one down quark snapped together, forging a proton. Conversely, two downs and one up form a neutron. Since up quarks carry a positive 2/3 charge and down quarks negative 1/3, the proton sums to positive 1 and the neutron exactly 0. By locking these chaotic subatomic fragments into stable, predictable units, the universe laid down the physical bedrock required to build every element that exists today. With protons and neutrons established, the timeline jumps to a period known as Big Bang nucleosynthesis. This phase spanned from exactly 10 seconds to roughly 20 minutes after the initial eruption. Inside this 20-minute window, the ambient pressure of the universe was still immense. The newly minted protons and neutrons were violently driven into one another. These high-speed collisions forced the particles to fuse, forging the first atomic nuclei, specifically creating hydrogen, helium, and traces of lithium. This text highlights the exact elemental mass ratio. The pristine early universe settled into a structural balance of roughly 75% hydrogen, 25% helium, and trace lithium. The flowchart below illustrates the sequence: pure quarks to hadrons directly into light nuclei. If the temperature or pressure during this 20-minute stretch had been even slightly different, those protons and neutrons would have remained scattered. Nucleosynthesis provided the mandatory physical bottleneck required to produce the fuel that powers stars. Fast forward hundreds of thousands of years, the expanding universe finally cooled down enough for passing electrons to be captured by the gravitational pull of those nuclei, locking them in to create the first complete neutral atoms. Over millions of years, giant clouds of these newly formed atoms accumulated. They collapsed under their own gravity to ignite stars, structure vast swirling galaxies, and ultimately build rocky planets. Look at a distant nebula, the iron in the Earth's core, or water in your own body. Every piece of ordinary matter relies on the exact same subatomic recipe. Our physical existence, and the entire observable cosmos we inhabit today, is simply the physical legacy of those quarks successfully finding each other and holding fast in the opening minutes of time.